Hello, everybody, and welcome to NME 2305 Material Energy Balances. We're continuing our lectures on energy balances, and so this is Energy Balances Part 2. I'm your Professor D.A. Robertson, and you can reach me at the email address. What we've covered so far, you can refer back to the first lecture if you've forgotten or you just didn't see it. We've talked about types of energy, so kinetic energy, potential energy, internal energy, and heat and work. And we're going to cover some more. And we're going to talk about the first law of thermodynamics for a closed system and the first law of thermodynamics for an open system. And we're going to kind of go through some problems to kind of help reinforce some of these concepts. Kind of recapping a little bit of the end of the last lecture, we're talking about PV work. And so PV work of the balloon expands against the surroundings, so it's actually performing some work against the surroundings. We talked about these four processes: isochoric, isobaric, adiabatic, and isothermal. I didn't talk about this enough. Ideal gas law, I have my edits from PowerPoint, I guess, telling me I spelled everything wrong. But don't forget the ideal gas law, and we have different flavors of the gas constant that come in handy with some of these calculations. And this was kind of the last problem we worked out at the end of lecture 1. So refer back if you're interested. Enthalpy, we're going to talk a little bit more about enthalpy, and enthalpy is total energy in the system. It's a state property, so enthalpy depends on what a substance is, what the temperature is, and what the pressure is. I will go ahead and give a spoiler. Now, most of the problems we do here, in fact, all of them, I believe, are constant pressure problems. It's an extensive property, so it's dependent on how much of a substance there is. And so if I have 10 gallons of water, the enthalpy of those 10 gallons is 10 times greater than 1 gallon of water. The difference between an extensive property and an intensive property is density is an intensive property. So 1 liter of water is going to be the same density as 1 milliliter of water. Kind of going back to extensive properties, 10 kilograms of coal is going to release 10 times as amount of energy as heat as 1 kilogram of coal. And we'll explore this when we start getting into reactive energy balances as well. There's types of enthalpies that we will kind of talk about. So there's enthalpy of transformation. It's also called heat of transformation. That could be a phase change, and phase changes can be crystallographic. So if you remember titanium, you can go alpha beta titanium. So you can go from hexagonal closed pack to FCC, face-centered cubic, BCC, body-centered cubic. I made a boo-boo. And there's an energy associated with that. There's enthalpy of fusion, or heat of fusion. It's also heat of melting. Enthalpy of vaporization, which is boiling, and enthalpy of sublimation, which is skipping. So you can go from solid to gas, and that's sublimation. And there's a different energy associated with that. Specific properties, an extensive property divided by a quantity, a flow rate divided by a quantity. The term specific enthalpy is applied if we're talking about specific enthalpy. And so joules per mole would be 1. And so a lot of times we get values in joules per mole, and then we're given moles, and so we have to cancel out the moles to figure out total heat. The specific enthalpy, an example again, is joules per mole. Thermodynamic tables, and so there's an example of calcium. I uploaded to Blackboard, and if you've not downloaded or opened up that table, I would ask you to pause this lecture here so you can kind of have it, because a lot of the problems that we're going to work out deal with that table. Units are specified on the table. I have put, and I think I spelled altered wrong, excuse me, but I put a little Excel app on Blackboard to kind of help you with some of the problems. And I also post individual tables for specific problems. A lot of times people have problems with this. I've tried my best to kind of alter it to make it a little more usable. One thing is this utility. It's an Excel-based utility, but it doesn't work on a Mac. I've had a lot of students over the years complain. And so I tend to give you the tables so you can solve your problems. The standard unit of temperature is Kelvin, so we're going to be working in kelvins, or Kelvin, degrees Kelvin, if that's correct. The standard amount is gram mole. Okay, so we've done all this stuff where we're using kilogram moles and sometimes pound moles and other calculations. For this, we're going to be doing gram mole for the rest of the class pretty much. And the unit of energy is joule. I think I have one or two problems I throw at you that have different units, but for the most part, we're going to be using joules. And there's different equations for different states. Solid, liquid, gas is one, and also crystallographic state is another. So there's different equations, and what equations are we talking about? We'll look at the table, and we'll look at a quick example on this slide. Here's an example of the calcium table, and it's kind of small, but let me try to sensible heat is the change in enthalpy required when a substance is raised to one temperature to another. It's called sensible heat because it can be sensed relative to the enthalpy at room temperature. And you'll see in some of these calculations, I tend to use words like pay respect to room temperature enthalpy, and that'll be more clear after we work some of these problems. So we're going to work out a problem right now, and we want to know what is the heat required to raise 500 grams of calcium from room temperature to 1800 Kelvin. We also want to note that the standard temperature, or STP, standard temperature, is 273 K. Here we're using room temperature, which is 25 degrees Celsius or 298 Kelvin. All right, so we're going to use our sensible heat table. It's the simplest way to do calculations is using the table. We're also going to have examples of using equations as well. But the first thing we're going to do is we're going to use our table, and we're going to raise 500 grams of calcium from room temperature to 1800 Kelvin. And we're a little blurry, so let me try to fix that for everybody. There we go. The first thing we got to do is find the moles, and that's kind of a common theme. So first find the moles, or the number of moles. If you remember, we find the number of moles using the atomic mass of calcium. You can get that off a periodic table. You can also get it off of the thermodynamic table here at it's called GFW. You can also get the number of moles off of that GFW. So we can use our basis of 500 grams. It's given. And we know that 1 mole of calcium is about 40.08 grams of calcium. I didn't put that there. And then, so grams of calcium cancels. And so we end up with 12.47 moles of calcium. Now the sensible heat which is denoted by H2 minus H298, we can kind of rewrite it if we want. H1800 minus H298 if we want to be proper, because we're getting the sensible heat of calcium at 1800 degrees C because we raised it from room temperature. That is equal to 29061. I think I missed a zero there. 29209. Excuse me. Joules per mole. I got that off this table here. And if you can't see it, it's okay. You should have a copy as well. 209061 joules per mole. It's a sensible heat of calcium at 1800 degrees Kelvin. So we just multiply our number of moles by that. So we have 209061 joules per mole times 12.47 moles of calcium. And that equals to 2606,230 joules. Maybe a little bit different if I rounded poorly. You can also rewrite that in terms of kilojoules. Uh, 2606.23 kilojoules. All right, so I kind of messed up this slide, but that's okay because I'm just giving you a spoiler of the problem we're going to work out next. But heat capacity, so enthalpy is really just the integral of constant pressure heat capacity, our Cp delta T. We're going to use the heat capacity equation on our table, the calcium table, to calculate what the enthalpy of calcium is at 542.6 Kelvin. This is the enthalpy equation, and we have this form, and I'll talk about the form a little bit more. 542.6 K, there's different equations for different temperature intervals. These temperature intervals are denoted by the phase change. So we know at 720, there's the alpha to beta transition of calcium. We're at 542.6 K. So we want to use this first equation, or the coefficients to fill in to make our equation rather. And we'll see that. All right, so now we want to, we want to calculate the enthalpy of calcium at 542.6 Kelvin. And we were given the heat capacity equation off the table. And 16.03 plus 2.15 times 10 to the negative 2 plus 2.55 times 10 to the 5, and I'm reading the variables, I'm sorry. This first one is 2.15 times 10 to the negative 2t, 2.55 times 10 to the 5, t to the negative 2. We want to integrate this from 298 to 542.6. Remember, this is an isobaric process. It's a constant pressure heat capacity. I'm just kind of throwing that in there. So then we integrate this, and then we can kind of rewrite it in terms of 16.03 T. So this is the integrated equation plus 1.075 times 10 to the negative 2 T squared minus 2.55 times 10 to the 5, excuse me, 10 to the 5 t to the negative 1, and 298 to 542, 0.6. So we can, this is the integrated equation. I'll spare the kind of intimate calculations, I guess. If you remember calculus, you're gonna plug in 542.6 and then subtract into this equation, then plug in 298 and subtract that value from the value you got from 542.6. And so it's 1139 2.88 minus 4875.88. And that gives me 6517 joules per mole. If we want to go back to the other problem we worked out and say, hey, okay, so what if we raised 500 grams to this? You could just take your grams, 12.47 moles of calcium, and you can multiply it again by 6517 joules per mole. And let's work that out. I got 8126.99, 266. So let me write it out because I'm not talking well. Let's just say if we considered that, but this is the answer. This is actually the enthalpy of calcium at 542.6. I kind of expanded a little bit, just to kind of make it a little more practical. But again, we're integrating the heat capacity equation to get enthalpy, and we'll carry on. All right, so we just worked out this problem. What is the enthalpy of calcium at 542.6 K? We're using the enthalpy equation, so we had to integrate. One thing I need to point out is if you're given the enthalpy equation, the HT minus H298 equation, which is really just the integral, and then you get that constant to kind of put everything together, you can just plug in 542.6 into the enthalpy equation. You don't have to integrate. So be sure and pay attention if you're given the heat capacity equation or the enthalpy equation in these problems you worked out. If you're given the enthalpy equation, you don't have to do any integrating. You just plug in 542.6 for your temperature T. If you're only the next thing we're going to talk about is Kirchhoff's law, and it doesn't matter the path between the points. The change in enthalpy will always be the same, and this is kind of my crude drawing. We're still getting from point A to point B, and so we kind of took this kind of roundabout path, and it's kind of almost a sinusoidal path, but we're still getting from point A to point B, so the change in enthalpy is going to be the same. That's Kirchhoff's law in the most high-level, simplest form possible. We're going to work this problem using the tables, and so I want to raise 500 grams of calcium from 600 K to 1000 K. So I have some calcium. I'm already hot. I'm already above room temperature, and I want to get hotter. And so we'll work through how to do that using Kirchhoff's law and the sensible heat tables. All right, so we're doing a simple Kirchhoff's law problem here. We're raising 1 mole of calcium from 600 K to 1,000 K. And so what's the trick here when we're using the tables and we're using sensible heat, you always kind of want to think of it in terms of giving respect to room temperature is kind of how I tend to put it. And so we want to get to 1,000 K. We're at 600 K, and everything's with respect to 298 K. And so it helps to start getting in the habit of diagramming your processes because it kind of helps keep things clear. And this problem is pretty simple because we're really only going from one temperature to another. But we have these, again, this is still referring to the calcium table that you all have a copy of. And so we have to pay attention to some kind of critical values. And so let's think about what we're doing. So if we want to use these tables, we can't just go from 600 to 1,000 Kelvin. Okay, we have to pay respect to 298 K. So the first thing we have to do is first cool to 298 and then heat to 1,000. That's the way that these tables work, basically. So now we end up with two enthalpies that we'll have to calculate. So the first thing we're doing is H. So we can kind of put it backwards, or negative. Basically saying this is the negative enthalpy value of 600 K because we're actually cooling it. Okay, so we get that value off the table, and the value on the table is 8184. We can kind of denote this as delta H1 and say this equals 8184 joules per mole. Again, we're cooling it, so it's negative. Delta H2 is raising it from 298 to 1,000, so it's H1000 minus H298. And that equals, if I look at the table, I got 1,000, so 22636 is the number I got, equals 22636 joules per mole. So delta H total equals delta H1 plus delta H2. And so that equals negative 8184 joules per mole plus 22636 joules per mole. And we can add that together. And I got 30, oops, made a mistake. I got 14452, so 14,452 joules. Step one should always be find the number of moles. But we were told already we're raising 1 mole, so just to kind of keep it. I'm using 2 spellings of mole. That's embarrassing. So it's 14452 joules. Joules. All right, so we just worked out this problem, and here's a prettier diagram of what actually happened. So in reality, we were taking calcium from 600 K to 1000 K, but if we're using those sensible heat tables, we first have to drop the temperature from 600 K to 298 K and take that delta H. We then raise from 298 K to 1000 K and take that delta H. So then we just add them together, paying attention that since we were dropping the temperature, that this is a negative value. Okay, so one thing I kind of want to point out with my kind of prettier diagram is you want to get used to the strategy of adding component enthalpies. And we'll have another example. A little bit more on the thermodynamic data. So there's different sources. And so these constant pressure heat capacity equations have different forms. And so there's two forms in the Felder and Rousseau book that we kind of refer to. So there's form one where you have A plus BT plus CT squared plus DT cubed. In another form, A plus BT plus CT to the negative 2. Always remember enthalpy is the integral of your heat capacity equation. If you're given the heat capacity equation, you have to integrate it. If you're given the enthalpy equation, you don't have to integrate, you just plug in temperature. So don't ever forget that. The US Bureau of Mines equation is one that the thermodynamic tables that we're using, at least in this first part of class 4, are based upon, and I pay a little bit of homage to US Bureau of Mines. They're not around anymore, but they did a lot of work calculating the constant pressure heat capacity for a lot of substances, and we have their data to take. And so for inorganic materials, your enthalpy form is AT plus BT squared plus CT to the negative 1 plus DT to the 1/2 plus ET to the cubed plus F, which is always a constant. At different states, you may use one or more of these A through B coefficients. The heat capacity, put the heat capacity equation first because this is the integral. But anyway, the heat capacity equation is of this form, and we've already played around with both of these a little bit, or at least seen them. And again, to solve for enthalpy, it's the integral of heat capacity. If you're given this heat capacity equation, again, you just plug in T, just plug in chug. And so I'm kind of saying this is the integral of this equation is the integral of this equation. And so anyway, enthalpies of phase changes, and there is we're gonna see we're going to see kind of using multiple components to calculate the total enthalpy. But energy associated with phase changes, crystallographic changes, melting, boil, and we kind of went over that already on the table. Alpha calcium is FCC, while beta calcium is FCC. So the primary phase is FCC. And we saw that there's a phase change. Again, here's the table. And hopefully you have at least a standalone digital copy. Other enthalpies, I talk a little bit about conductive ink, and where we got to over 200, we start seeing some grain growth and stuff like that. So there's some exothermic energy associated with that. So kind of tying in a little bit of research with some of these learning activities. So now we're going to do a more complex problem where we're calculating the change of enthalpy using the heat capacity equations, and we're raising calcium from 298K to 1800K. And one thing I need to point out is that we have to use all 4 of our constant pressure heat capacity equations, and we also have to take into account the enthalpies of phase change listed on the table. And so if you remember, we had the crystallographic change from alpha to beta. We had the melting phase change, and then we also had the heat of vaporization. And we'll see this problem worked out shortly. Alrighty, so what we're going to do now is we're going to heat calcium from from 298K to 1800K, using the heat capacity equations. So constant pressure heat capacity equations. So we said on the previous slide that we have to use them all, and then we also have to use the phase change values. And so I'm using what's becoming my tired sensible heat table. So all these heats of there's a phase transformation heat, a melting temperature, and a boiling point. So it's all the phase change heats that we have to kind of take into account when we calculate the enthalpy of raising calcium from 298K to 1800K. So we have to use all the equations. We already know it's easy to use the table, but we're hardworking, mighty fighting, dynamiting mining engineers. So we want to go ahead and kind of do it the hard way, because what if we don't have a computer? Anyway, so we want to break it up into separate enthalpies. And so the first enthalpy that we have to use is over the interval from our table from 298K to 720K. And I guess I should be more specific, 298.15, but I always drop off to 0.15. Maybe it's bad practice. So delta H1 is the integral of 298 to 720K of the heat capacity equation, and we're in alpha mode here, so at the primary phase of calcium dt, so with respect to temperature. Alrighty, and the equation that's given off of our table is, and I'll leave off some decimal points for brevity, but it is about 16.03 plus 0.02 plus 0.02 T, excuse me, and plus 25524 excuse me, 224 T to the negative 2. So that gives us an integral of 16.03 T. We've seen this equation before, plus 0.0175, add some decimal points there, excuse me, T squared minus 255, 224, T to the negative 1, and sorry, I'm after the engineering paper margin here, over the interval 298 to 720. I'll spare again the calculation of this. Delta H1 equals, I got about 11 joules per mole. Delta H2 is the alpha beta or alpha beta transformation, whatever you want to call it. And off of the table, it's 920.48. Delta H3 now, so we have two delta H's. We've calculated one and we've read one off the table. So we have two delta H's. Delta H3 is the integral between 720 and 1112 of CP dt. So now we're in the alpha phase of our material. And that is the integral of negative 0.37 t plus 0.02 Oh, I made a boo-boo. That's not there, so we're going to get the integral. So excuse me, so it's the integral of this equation. So negative 0.37 plus 0.04, and that's t. And that's it. So it's a smaller equation, and we're going to end up calculating 0.0206 t squared over this interval. Don't ever create calculus. And this means delta H3 equals to about 19098. Joules per mole. Delta H4 is the heat of melting, basically. And it's the solid-liquid transition. Here it's denoted by the melting point on your table. And if I can read, it's at 8535.36. Delta H5, we're almost there. Delta H5 is the integral of 1112 to 1757, and the equation I'm looking at is this third one on your enthalpy values here. And it's a nice short equation of it's the integral of 29.29 dt, and so that's 2. So delta H5 happens to equal, if I've calculated right, 18891 joules per mole. Delta H6 is the heat of vaporization. And that again is off the table, and it's a rather big number. So 153,243. 153,243.18 joules per mole. And delta H7 is our final integral. And that's the integral of 1757 to our terminal temperature that we're wanting to get to, 1800 Kelvin. And that is the integral of 36.14 plus, actually minus 0.014 t squared. All right, so we're calculating delta H7, and that gives us the integral of 36, or we're getting the integral here, 14 minus so 36.14 t minus 0.007 t squared, or the interval of 1757, 1800. So delta H7 equals negative 17.94 joules per mole. You add them all up. Equals the sum of delta H equals delta H1 plus delta H2 plus delta H3 to delta H7. Keep it for brevity, and so I added them all up, and delta H, or we call it H 1800 minus H298 equals 209,874. And I take a look at the table. I'm a little off. The table says 209,061, so it's pretty close, and I maybe a little sloppy with the rounding. I'm not an order of magnitude off or anything like that. One thing I kind of want to point out is you have just one equation, and you could also just plug in to this equation, and I'll talk a little bit more about it on the next slide, and see if this is, you can pause it where it's not so blurry if I move my hands off. All right. Excuse me. So now let's do a non-reactive mass and energy balance. It's more of a non-reactive energy balance, but anyway, we want to look at the heat equation, so we're going to be using a specific, we're going to be using the enthalpy equation to solve this one. And so we have 6 steel slabs that we want to preheat because we want to put it through a hot roller to roll them down. And so we have 6 steel slabs. They're 12 foot by 4 foot by 1 foot. And then we want to heat it up from 77 degrees Fahrenheit to 2400 degrees Fahrenheit for hot rolling. We're going to be using the sensible heat equation for iron, so it's easier to assume that steel is iron than to incorporate all the constituents or microconstituents of steel. So this is the coefficients we're going to be using, and you'll see why we picked this one, because we converted from Fahrenheit to Kelvin, and you'll see how this problem is worked out shortly. Okay, so we have our 6 slabs of steel. Okay, some real metallurgy work here. They're 12 foot by 4 foot by 1 foot, and we're raising it from 77 degrees Fahrenheit to 2400 degrees Fahrenheit. Ooh, changing units. I have to do some conversion. So this is steel. One thing we're going to assume that this is iron. So we can just use one table. Maybe it's a low carbon steel. But let's just go ahead and assume it's iron, and we've seen that we're going to use the sensible heat equation. We're not using a heat capacity equation this time. So we're going to use the heat equation given to us in our slides. So we have 6 slabs of steel. We're assuming it's iron. So we're gonna do everything based on iron. And so step 1, we want to calculate the number of moles. And that's, again, a kind of common theme, calculating the number of moles. And so we have 6 as our basis, and it's 12 foot times 4 foot times 1 foot, and that's a cubic foot, and that probably should be a little bit better in terms of units. So we have 12 times 4 times 1, those are all feet. We have cubic foot per slab, so we can cancel slabs. And so cubic foot per slab. I'm a little sloppy with this one, I apologize. We can use a conversion factor, 0.0283 cubic meters per cubic foot. And so that gives us 8.15 cubic meters. And we're going to assume it's iron, okay? We want to get to volume to mass to moles. And so we're going to go volume to mass. And we've seen similar calculations. So to get to volume, from volume to mass, we need density. To get from mass to moles, we need atomic mass. And so we can get this off of tabularized values. So we can start off with 8.15 cubic meters of iron. All this information is also on the thermodynamic table. So I showed kind of a truncated version of the thermodynamic table showing just the sensible heat equation, but the bigger version of that table, and I'll upload that, also has the atomic mass and the density of the material as well. And so iron is 7.874 grams per centimeters cubed. 1 centimeters cubed equals 1 times 10 to the negative 6 meters cubed. And there's other ways to convert this as well, you guys all know that. So 1 mole of iron is 55, have this one memorized, I think, 0.85 grams of Fe. And so this equals 1.5 times 10 to the 6 moles of iron. The other thing that we had odds, so we know that this is room temperature. So we already know that 77 is 298 K. We already know that. The other temperature we have to convert is 2400 degrees Fahrenheit to kind of figure out what temperature we want to use, because these equations only work with Kelvin. And there may be another way to generate a different unit equation, but it's always better to work everything in Kelvin anyway. So we want to know what the temperature of 2400 degrees equals to in Kelvin, and some of you do this conversion a lot. And so we want to first convert to Celsius, then we can convert to Kelvin. And so 2400 degrees Fahrenheit, and the conversion from Fahrenheit to Celsius is degrees Fahrenheit minus 32 over 1.8, and so that equals 1315.56 degrees Celsius plus 273.15 to get to Kelvin. And I get 1588.72 Kelvin. Sorry, I'm moving out of my little margin again. So we can just plug it into the sensible heat equation that we got. So the sensible heat equation, and let me take a quick look at it again. Slow. Is 23T plus 0.0044 T squared minus 498,013.15 T to the negative 1. And also we have our constant plus 1.5 and so this is the constant. All right, so if we just plug in 1588.72, squared minus 498,013.15 over 1588.72. Gonna have to add this on 1501.57. I get 834.3 joules per mole. And then we multiply that by 1.5 times 10 to the 6 moles. And we're assuming iron this time. We got the sensible heat of iron. And I got 5.61 times 10 to the 10 joules. Lots of heat there to heat these slabs up. All right, so we performed a energy balance by heating up some steel, and we assumed it was just iron. One thing I need to kind of point out is that most input streams consist of mixtures. So we've seen this. We've seen oil and water. We've seen air, N2 and O2. We've seen our old friend zinc and cadmium, which we can separate with a distillation process. One thing also to point out, and you'll have a problem to work out, is chemical compounds. So let's look at cementite Fe3C. Will heat up differently than a mixture of iron and carbon. And so if I have 100 grams of Fe3C and I have a bag of iron and carbon of the same stoichiometric ratio, those two things are going to heat up differently. Heat difference, there's some slight differences between two mixtures of air. So we use 2179 mostly in this class. We kind of leave out the argon, and but there actually is a slight difference in the heat of heating up these two mixtures. Kind of going back, just kind of remembering, what we're kind of talking about. We're seeing this again, how we have mass crossing system boundaries, and we have heat and work crossing system boundaries. So the only way energy crosses system boundaries is through heat and work. If you have a closed system, things are a little bit different. So the energy change of the system is equal to the negative of the energy change of the surroundings. This is kind of a concept that we want to kind of take home. The internal energy of the process stream entering the system is loss of the surroundings. Work done by the system on the surroundings is the negative of work done by the surroundings on the system. Kind of just think about it. The heat which warmed up the still slabs had to have come from somewhere. So we're going to look at another problem. We're going to look at an electric arc furnace. And I worked in a steel mill once, and I remember walking into the melt shop on pretty much a daily basis, and you just feel these electrodes, you feel them in your chest. It was actually kind of cool. So let's work out a problem where we're transferring electrical energy, and let's take a look at it. So we have 150,000 kilograms or 150 metric tons of scrap iron, and we're charging it to an electric arc furnace. We have this electric transformer supplying 45,000 kilowatts to the electrodes. The final temperature of the scrap iron is 1650 C, or more to our liking, 1923 Kelvin. We're going to assume all the electric current is converted to heat, and how long will it take to get our iron to the final temperature? And so let's work this one out, shall we? All right, so we're looking at our scrap iron in an electric arc furnace. One thing we kind of want to point out is we're assuming pressure and volume aren't changing while we're melting our scrap. We have an electric arc furnace, and so delta U equals delta H, and that equals our total change in energy. Okay, so enthalpy is pretty much the only change. So we're putting in electrical energy. So in this case, delta H equals amount of electrical energy. So the delta H equals our electrical energy. And so if you go back to the previous slide, we had 150 kilograms of scrap iron. We're charging it to a furnace, 45. It's actually 150 metric tons, so it's 150,000 kilograms of iron. Excuse me. We're charging it to a furnace. We hit it with 45,000 kilowatts, and we get a final temperature of the steel of 1650 centigrade or 1923 Kelvin. And we're assuming no loss. This is kind of we're hoping for the best, so we're assuming no heat loss. And so to tackle this problem, the first thing we do is always first find the moles. So I'm going to first find the moles. And so we have 150,000, excuse me, kilograms of iron. And we're going to kind of do our conversion this way. The reason why I do things in gram moles for these problems is because our table gives us everything in terms of gram moles, in case you're wondering. So 55.847 grams of iron, and so we start off with kilograms, and so we have to do our conversion. Grams in 1 kilogram, so don't ever forget that. And I got 2.68 times 10 to the 6 moles of iron. Moles of iron. We're using our sensible heat equation for iron again, and so our sensible heat equation for iron off the same table we used for the 6 steel slabs problem is 46.024 T minus 10916.06 as the constant, and that's because we're at this high temperature. So we're heating it up to 1923. So we use the appropriate equation for this that takes into account 1923 as our interval. So let's calculate the sensible heat at 1923. So that's just simply 46.024 times 1923 minus 10916.06, and that equals to roughly 77588 joules per mole. We already calculated the number of moles, so we're just trying to figure out how much heat, total heat in joules, and then we'll get to something else here very quickly, because we're wanting to know how long it will take to melt the scrap, and I'll go through the conversion pretty soon. But let's get to joules first. And so it is 77588 joules per mole. We calculated our number of moles, and that's 2.68 times 10 to the 6 mole. And so that's a big number. We got a big number. And that's 2.08 times 10 to the 11 joules. That's pretty big. So hey, let's figure something else out. So we were told in the problem that we supplied 45,000 kilowatts of energy. Okay, and so we want to find an equivalent conversion that'll give us something that we can use to cancel out kilowatts. okay? So we want to go from joules to kilowatts, hours, sorry, joules to, so the equivalent form of energy that takes into account kilowatts in joules is kilowatt hour. Okay, and hopefully I'm not making this more confusing than it needs to be. But we have 2.08 times 10 to the 11 joules, which we calculated here. And there's a conversion factor. 1 kilowatt hour is 3.6 times 10 to the 6 joules. So joules is going to cancel. So that equals 57777.77. So a lot of sevens, kilowatt hours. All right, so we want to end up with hours because we want to know how long, right? Let's do a little unit analysis. So kilowatts times hour is equivalent to joules, okay? It's a unit of energy, kilowatt hour. So let's divide by kilowatts to get that. And how many kilowatts do we have? Well, we said we supplied 4,500 kilowatts to this furnace. And so thousand kilowatts, excuse me. And that equals 1.28 hours. All right, so to get this much steel to this temperature, 1923, if we're supplying 45,000 kilowatts, it's going to take 1.28 hours to get to that final temperature. And hopefully this was not too confusing.